So I will first show you a brief history and the context where we developed this system. The concept, the originality or weirdness, if we can talk like this, and also the flexibility and fast deployment of this system, which is the key point of it. And after we will make a short turn about the application and performance, especially for mountain, complex area mapping, oblique mapping, and for high accuracy corridor mapping. There were some presentation talking about this. You will see also things, especially for Switzerland, and draw the conclusions. So first, Switzerland is a country of mountains, and conventional mapping got several issues, since first the fixed-wing aircraft got poor flexibility for natural hazards, for example, and it's expensive, it's inappropriate for small areas, it's expensive for this, and it's not suitable for accurate data in complex terrain with cliffs, steep slopes. You get not constant accuracy, constant density, so you need something that can do, for example, mapping for avalanche sites, and you need fast deployment. That means we're talking about 1 hour or 2 hours to get there and do the mapping. An affordable solution for small areas, high accuracy, better than 10 centimeters in altimetry, and designed for inaccessible areas and complex terrain. This cannot be with fixed-wing aircraft. We can do this with helicopter solution, but once again, using fixed system on helicopter, it's time for installation, and it prevents from fast intervention and flying flexibility. So the idea was to use the handheld system. You take it, get into the helicopter, and do the flight. A brief history here. It started now about 15 years ago in the Swiss Federal Institute of Technology in Lausanne, where we started with the classical photogrammetry, handheld photogrammetry with the lean-off cameras. The weight increases at the beginning with the first lean-off cameras, about 8 kilograms, and after we used the Japanese Tomtex camera with what 20 kilograms, integrate IMU GPS on it and handheld. At 20 kilograms, the handheld we can discuss because it's quite heavy. And in 2003, digital cameras bring the strong diet to the system, reducing the weight to only 6 kilograms for GPS IMU and camera. So it was really, really flexible. And after, once again, the weight increases with the lidar. We made the first step in 2004 with the Q140. And finally, in 2005, we created the company with the Q240. And in 2008, we bought the first VQ480. And now, 2011, we have the third system with the VQ580. Everything handheld, but now it's a bit heavier. The system was developed originally for avalanche volume monitoring in Switzerland to study the avalanche runoff. So we got this huge site with steep slopes, about 45 degrees, and we need to do the monitoring, the data acquisition of the surface before and after the avalanche, and we trigger artificially the avalanche. And we can measure the volume and the motion of the snow, and then after we can use it in the simulation models and everything. So that was the purpose. The requirements was better than 10 centimeter accuracy, independent from topography, and inaccessible, really fast setup. We're taking here about 1 hour to be ready and do the mapping, and affordable cost for such small areas. And the concept that if you get, laser pointer. If you get standard nadir view lidar, you get some decreasing of the accuracy at the bottom of the slope, and if you get some cliffs, you can have some gaps in the data. So the idea is you turn the system and the slope looks flat. And if you can turn it adaptively to the slope, you can have constant accuracy and density in almost all the areas. So that's why we are made handheld sensor head and helicopter based. The concept here, you can see you're sat on the side of the helicopter. You can use different type of choppers. Here Mi-8 in Chernobyl, standard squirrel, Vallet 3. You can see more, a lot of helicopters. It's only 30 minutes to be ready. You get to the helicopter, 30 minutes after you can take off. And okay, you need one operator and one people inside for checking the data acquisition and everything. The integration, the advantage here, you get all the sensors into a single block. And with all the presentation, we saw always the IMU, the laser, but never the GPS antenna on the chopper. And usually it's far from the system, probably on the tail or in the front. And it's a big lever arm, and the chopper is not rigid enough. And with this system, we just have 1 meter between the GPS antenna and the system, and it's into a rigid assembly. So you can turn the system, the GPS antenna is turning with, and you get no motion between sensors. It's very compact. It's an adaptive way. You can turn the system and fit to the slope within a range of 45 degrees, which gives you a lot of range for slope. And you can make vertical mapping, oblique, terrestrial view for a cliff. And it's suitable for 1 to 5,000 hectares with big lasers, but okay, we are more focused in smaller areas. Regarding the performance, it's quite similar to the lidar mapping. It only depends on the height, especially with tactical grade IMUs. Now with the VQ580, we got the navigation grade IMUs. It changed completely the data set, especially for the heading. But usually for our range between 300 and 500 meters above the ground level, we got such type of accuracy for relative accuracy and for absolute accuracy, depending on road or smooth area, snow, grass, rough. It's always below 1 centimeters at 300 meters above the ground. So here, a few examples regarding their oblique mapping. With the application field is the terrain evolution follow-up time series, phenomenon modeling for simulation, rockfall simulation, calibration data, risk mitigation, and also for inventory disaster, post-catastrophe database, quantity damages. You can, if you got something that is ready, maybe a few hours after an event, you can do this. You get a chopper available, you can go and do it. And here we can produce such data. That means the cliff, for example, where we scan it obliquely, and then you get all the overhang parts, and you can model the caves and everything for geologists or for rock falls. For glacier monitoring, that's a topic in Switzerland, many glaciers, and there are some that are studied every year or every periodically. For example, this one in the south of, southern Alps of Switzerland, where we studied in 2006 and also in 2010, and the melting is, you can see the difference here, and when we put some numbers, it's a bit scary with 2.5 meters of melting per year at 3,000 meters altitude. So, and you can also detect